Hello there chemistry students. This video takes a look at intermolecular forces. Please subscribe to the channel if you'd like further updates, and if you have any questions please post them in the comments and I'll do my best to answer them. If you've got any requests for further questions, different topics, let me know and I will try to upload some of your favourites. So we're going to be looking at molecular forces. So the topics you want to be looking at and revising before the attempt on this question will be shapes of molecules, dot and cross diagrams, lone pairs and bond pairs of electrons, the name of shape and bond angles, electronegativity, how that leads to polar bonds and polar molecules, and ideas of symmetry. You also need to know the types of intermolecular force. This question doesn't look specifically at hydrogen bonds, although you need to know it, but it will look particularly at induced dipole-dipole and permanent dipole-dipole intermolecular forces. Okay, let's take a look at the first question. Have a look at the question, pause it, and when you're ready for the answer, press play. Okay, welcome back. Straight ahead definition for 1 mark. Electronegativity is the power of an atom to attract a pair of electrons in a covalent bond. Now this gets you marks, but it also should jog your memory and is relevant to the next couple of sections of this question. So we're going to use this idea of electronegativity to explain how permanent dipole-dipole forces arise between hydrogen chloride molecules. Have a go at the question, press pause, and when you're ready, press play. Okay, welcome back. So we've got a difference between electronegativity in the hydrogen atom and the chlorine atom. The chlorine is more electronegative than the hydrogen. So this leads to slight positive and negative charges on the hydrogen and chlorine atoms. The hydrogen is slightly positive and the chlorine is slightly negative. So there will be an attraction between the chlorine atom of on one molecule and the hydrogen atom on a neighbouring molecule. So we've written that down there. A diagram is always useful if you can put a diagram in. Make sure it's large and clear and labelled. And the intermolecular force I've shown there with that dashed line. So that's our permanent dipole-dipole force between the two molecules. It's worthwhile labelling it up, and there it is. That's the permanent dipole-dipole force. Okay, a 4-mark question now. Have a read, press pause, and when you're ready, press play. Okay, welcome back. So shapes of molecules can often be quite challenging. There's a lot of content that you need to know, and you also have to visualize these molecules in 3 dimensions. So I've put together, before we take a look at this specific question, just some general ideas of what you'll need to do in order to attempt questions like this. To start off with, you need to find a total number of bonding pairs or bonding regions and lone pairs of electrons. This question doesn't have any double bonds in any of the molecules or triple bonds for that matter, but a bonding region will act in the same way as a bonding pair of electrons. A dot and cross diagram will help you to be able to identify the total number of bond pairs and lone pairs. These are very useful, especially when starting off, so you might need to review how to draw dot and cross diagrams. Next, you simply need to know the names of the shapes and bond angles. This question didn't ask us for bond angles, but it could have done. So make sure that you are aware of all those. It's just a case of memorizing content. And finally, possibly the most challenging part of this question is being able to spot if a molecule has a permanent dipole overall. To have a permanent dipole overall, you need to have polar bonds, and the molecule needs to be non-symmetrical in 3 dimensions so that the bond dipoles don't cancel out. And we've got some animations that help us with that. Okay, so to start off with, let's have a little look at silicon tetrahydride. Is that? Don't know. SiH4. We're going to have 4 bonding pairs and 0 lone pairs of electrons. The silicon has got 4 outer shell electrons, the hydrogen's got 1 outer shell electron. So We've got 4 covalent bonds and 0 lone pairs. So if we look at that in 3 dimensions, each one of those silicon to hydrogen bonds is indeed polar, but hopefully we can see that there's no one particular side of that molecule which is going to be more positive or negative than the other. So, overall the SiH4 molecule is not polar. Let's take a look at pH3 now. Phosphine, I think that is. Here I've used yellow to represent a lone pair of electrons. We've got 3 bonding pairs of electrons, so 3 to pH bonds, and we've got 1 lone pair. So the phosphorus is in group 15 or group 5 outer electrons. So it's got 3 of its electrons are being used up in covalent bonds, and the 2 other electrons are a lone pair. And if there was a positive charge on the right hand side of the screen, the lone pair of electrons and the slightly negative phosphorus will go to that positive side. So overall in 3 dimensions this is not symmetrical, so the bond dipoles do not cancel out. So the phosphorus, 3 bond pairs, 1 lone pair, is a pyramidal shape, and it has got a permanent dipole overall. BeCl2, beryllium dichloride, 2 bond pairs, and it is also got no lone pairs. It's linear. Because the beryllium atom is so small, the beryllium just having 4 electrons around it is quite stable like that, it being electron deficient as it is. So it doesn't need to gain a full octet. And our beryllium dichloride molecule, we'll have a little look at it. It's not really got a positive end or a negative end. So the bond dipoles act in opposite directions, and so the dipoles do cancel out. It is kind of symmetrical overall in 2 dimensions. So that would be linear and 180 degrees the bond angle there. Finally, CH3Cl. So there I've used the yellow to represent the chlorine. So in this case, it's similar to the phosphorus really, but we've got 4 bond pairs, 0 lone pairs. So the shape is still tetrahedral, but the chlorine being more electronegative, there we go. If there's a slight positive charge on the left-hand side of the screen, the molecule would move in that sort of orientation. The chlorine going towards where that positive charge would be. So we've got a 4 bond pairs, but the molecule is not symmetrical in 3 dimensions. So it is polar overall. Okay. So let's take a little look at the table again. If you didn't have a chance, maybe, or you weren't sure before, maybe you'd like to pause it now and see if you can fill out the details. Okay, welcome back. So the name of the shape, first of all, for 4 bond pairs and 0 lone pairs, 3 bond pairs and 1 lone pair, 2 bond pairs and 0 lone pairs, and 4 bond pairs and 0 lone pairs. So the SiH4 is tetrahedral, the pH3 is pyramidal, the BeCl2 is linear, and the CH3Cl is tetrahedral. In terms of the permanent dipole, we'll do the bond angles first of all, although this question didn't ask for it. Tetrahedral is 109.5 degrees. Pyramidal is 107. We reduced the bond angle of the tetrahedral shape by 2.5 because the lone pair of electrons will repel more than bond pairs. BeCl2, the bond pairs repel equally, giving us 180 degrees, and tetrahedral is 109.5 again. The SiH4 is symmetrical in 3 dimensions. The dipoles will cancel, so that has got no permanent dipole. Same is the case for the BeCl2. The bond dipoles act in opposite directions, so they cancel out. It's symmetrical, no permanent dipole. The pH3, however, does have a permanent dipole. as does the CH3Cl. Hope that made sense. If you have any questions, please feel free to post in chat. Don't forget, if you want to subscribe to the channel, you'll get updates, and if you would like any particular topics or questions, ask me and I'll do my best to get back to you. Thank you.